So how's everybody doing out there today? Well, welcome to day 11 of Corona Online School. And so this will actually finish up chapter 4 for us. So hopefully 4.1 went fairly well. So I was trying to ease you into 4.2 by trying to get you used to some of the terminology like at least, at most, less than, greater than, things like that, because that's going to come in handy for this section when we're trying to use these probability distribution functions to answer some questions about what are called binomial distributions. So just as a quick refresher, so remember a random variable, describes the result of an experiment. I think we had that definition in our last 4.1, and we've had it earlier too, so it just kind of keeps coming up again. So there's a certain kind of experiment that often arises that's kind of similar to this example, and these are kind of neat. So suppose you run a manufacturing plant making light bulbs. Through extensive testing, you found that the probability that a particular light bulb is defective is 0.02% in a batch of 1,000 light bulbs. What's the probability that one light bulb is defective? What about 2, 3, 10, fewer than 10, more than 10? So you see those words are starting to creep in and stuff like that. So these are what are called binomial distributions because basically there's two choices. There's either a failure or a success. So remember, bi means two. So in this case, like the light bulb being defective would be like the success, say, and the light bulb not being detective would be, or defective could be the failure, or vice versa. You could do it either way. So in this case, what we want to do is we want to figure out, well, what characteristics do we need to consider something to be a binomial experiment? So first thing it has to have is it has to have a fixed number of trials. So it can't just go on to infinity or anything like that. So like in the example above, they tested 1,000 light bulbs. So in that case, our 1,000 light bulbs would represent our n in this case. So there always has to be two possible outcomes. So again, there's a success and a failure. And so in this case, like the probability of success, if we call a defective light bulb success, then that would be that this is going to be a really small number. So our percentage of success, because we have to move this two places to the left, so it's going to be 0.0002. And then again, the nice thing is, remember, all probabilities add up to 1. So if the probability of success is 0.0002, then the probability of failure is going to be 1 minus that, which would be like 0.9998 in this case. So part 3, the probability of success is the same for each trial. So what that means is you can't have like, it can't be 0.0002 one time and then the next time you do it, it's like 0.5 or something like that. So it has to be consistent. So like when we roll dice, for example, like the probability of rolling a 3 is always 1/6. It's not 1/6 sometimes and 1/4 other times. So it has to be consistent all the time. So the trials are independent. So that, remember, that means that the first batch can't affect the second batch and things like that. So it's not like if we drew a card and then we threw that card away, like the next time the deck had less cards in it and stuff like that. So we need to make sure that it's like doing with replacement over and over and over again. And the random variable x describes the number of successes. And so again, the number of successes in our case is going to be whether the light bulb was defective or not. All right, so let's first look at example 1, which is for us to determine whether these things sound like they might be binomial experiments or not. So a coin is tossed 10 times. Let x be the number of heads that are actually flipped in this case. So the first thing we've got is, since we're flipping a coin and we're interested in knowing whether it's, I guess we'll look at the first thing first. So is there a fixed number of trials? So yes, we've got a fixed number of trials. So n would be 10 in this case. So that looks good. So are there two possible outcomes for each trial? Sure, because our probability of success, so let's call this success, which would be flipping a heads, is going to be 0.5. Our failure in this case happens to also be 0.5, which would be flipping a tails, but those are the only two possibilities. There's not three sides to a coin, or at least none I've seen or anything like that. So that looks good. Probability of success is the same for each trial, so that's true. So it's not like the first time you flip a coin it's going to be 1/2 and the next time it's going to be 1/4 or anything. It's always 1/2. The trials are independent because, again, if I flip the coin the second time, it's not going to affect the outcome of the first one. And the random variable describes the number of successes. So in this case, that's our random variable, and it says that we want our successes to be the number of heads. So this looks good. This is definitely a yes. All right, so let's look at number or letter B here. So 5 basketball players attempt a free throw. Let X be the number of free throws made in this case. So this one, turns out this one's like not going to be one, just because what we've got is we've got 5 different players that are involved. And so it could be that the 5 different players have different percentages for their free throws. Like maybe player 1 has a 90% success rate of making free throws, but player 2 might have a 47% success rate of making free throws. So the fact that each player could have a slightly different percentage makes this no good. Now, if we reworded it that one player shot 5 free throws, then we could actually make this into a binomial distribution. But the fact that it's 5 different players kind of screws it up because, again, there's no guarantee that all 5 players have the same exact percentage or probability of making a free throw. So again, if we wanted to word this so that it was a probability distribution, we just change it from 5 basketball players to a single basketball player shoots 5 free throws. And then this would be a perfectly good probability distribution. But for now, it's a no. All right, so let's look at letter C. So a random sample of 250 voters is chosen from a list of 10,000 registered voters. Let X be the number of people who support the incumbent mayor for re-election. So in this case, this one looks like it would be okay. So again, our fixed number of trials is going to be the sample. So it's not the 10,000. The 10,000 is the total number of people. So we're only talking about the n equals 250 in this case. And so since all we're asking for is the people who support the mayor, so there could be 27 people that are actually on the ballot. That's okay because the idea is you can, you either vote for the mayor or you're voting for one of those other 26 people. So it's not like you have to, like you say, I'm going to vote for candidate 22. It doesn't matter. You're either voting for the mayor or you're not voting for the mayor. So this actually works out good. So in this case, like the success would be voting for the mayor. Now, I don't know what the probability is, but somewhere along the lines, like they would probably tell it to us. But the fact that I can break this up into success and failure is all that actually matters. So not voting for the current mayor. And so is it the same for each trial? So, well, we don't know the probability, but if we did, it would be the same for each trial. Because again, it's going to be, well, I guess we do know. I guess it's 50%. So, because you're either voting for the mayor or you're not voting for the mayor. So there's a 50% chance you're voting for the mayor or a 50% chance you're not voting for the mayor. So it is the same. So are the trials independent? Yes, again, because just because I voted for the mayor doesn't mean the person behind me is going to be, any different. The probability hasn't changed or anything like that. And the random variable describes the number of successes. So again, that's this part of the problem here, which it does tell us that it's the number of people who support the incumbent mayor for election. All right, so very good. That is perfect. So let's get into some of the notation involving these probability distribution functions and stuff and the binomial distributions. So the question for a binomial random variable is always, what's the probability of X successes, or what's the probability of more or less than X successes? So again, this is why I was practicing these guys with you with the last section. So if we're looking for the probability of, say, exactly 5 successes, then we would actually just write it as the probability of x equals 5 exactly. Or if we use, say, less than or equal to 5, then we would set it up as the following inequality. So again, you could have every single possibility here, so just kind of keep that in mind. So we could have probability of x less than 5, probability of x greater than or equal to 5, probability of x strictly greater than 5. And in reality, you could even have, and we'll see some of these later, maybe something like 2 in between x and 5. So all of these, including the equals and the less than or equals, are all the possibilities that we can have for our binomial distributions and things like that. So, and all of them are going to kind of work out the same. They're all going to be based on the number of trials. So in this little example I did here, if there are 3 trials, then if we were to write out our binomial distribution table, like it would always start with 0, because there's always a possibility that no one is interested or there's 0 successes, the whole way up to where all 3 were successes. And then of course any whole number in between. And so what we did before is we were lucky enough and the percentages were always given for our binomial distribution, or it was easy enough to figure out, or for our probability distribution function, or it was easy enough to figure out. So for these, it's a little bit trickier to figure out what these probabilities of success are on a binomial distribution. So what we're going to look at is, here's a fancy little formula that will actually figure this out for you. But again, I don't want you to actually use this formula, but just to kind of point out what the different parts of it means. So in this case, we're trying to find the probability of exactly one thing occurring, because notice we use x equals little x. And so what we do is we're using this parentheses n over x. So this is actually what's called n choose x, which is exactly the same thing as our combination formula that we used in the last section. So you could actually rewrite this as n combination x instead of this sort of n choose x notation. It means the exact same thing. And then what we would do is take the probability of success, raise that to the x power, the number of successes that we're interested in, and then multiply that by 1 minus p raised to the n minus x. So the number of trials minus the number of successes that we actually want. And this would actually allow us to calculate this formula, this probability distribution function above. Now the downside is you would have to do it for every single trial. You'd have to calculate, x equals 0, x equals 1, x equals 2, x equals 3. So it gets a little tedious to have to actually write out the whole thing, especially if you're doing it by hand. So the goal is, what we're going to do is we're going to actually use a calculator to do this, because we're lazy and it's, we've got it available. Now, if you don't have a TI-83 calculator or something like that, and I forgot to mention, like, I've been kind of updating that Google Sheets as we go along. So I've added combinations and permutations to that same Google Sheet we were using earlier. So now I've added these 2 commands on the calculator, which are going to be the binom PDF and the binom CDF in this case. And so I'm going to show how to use it on the TI calculator. And then if anybody has questions about the Google Sheets and needs help on that one, just let me know and I can help you guys with that one also. All right, so binom PDF is when we want to use that when we're trying to find that the probability of big X is exactly, that doesn't really look like a big X, does it? Let's try this again. So big X is equal to little x. So in this case, that's when binom PDF comes in handy, because it's going to be, it tells us exactly what it is. It's a single value. Now binom CDF, so the C actually stands for cumulative distribution function. So that means it actually adds up all the values from 0 up to whatever you label x to be. So in this case, the way it looks like an inequality form is going to be big X is less than or equal to little x. So what it's really doing is kind of calculating like p of 0 plus p of 1 plus ... the whole way up to p of x. So if you notice, from above we had a couple different inequalities that we were going to work with. So that tells us the first two that were in our chart are taken care of right away because binomial PDF will always deal with this kind. Binomial CDF will always deal with that kind. But unfortunately, we've got four other inequalities that could occur. So what we end up having to do, and I'm going to show you in a little bit, is we have to get creative using binomial CDF to be able to answer these other questions. So let me leave that for now at the moment, and we'll come back to it when we get to that example. But just kind of keep that in mind. So, all right. So again, and if you notice, I've written the way you'll actually type this into the calculator. And so it's consistent regardless of whether it's binomial PDF or CDF. So N, remember, is the number of trials. And then P is the probability of success. And then the X is the number of successes. So it's always going to be in that order. So more than likely, if you make a mistake, you end up typing them in some kind of different order. And worst case scenario, you'll get an error. Best case scenario, you'll get some kind of an answer that pretty much probably makes no sense whatsoever. So always just kind of keep track. So the number of trials goes first, comma, the probability, comma, the number of successes. But again, I'll show you on the calculator as we're going through here, so that way you know how to do it. All right. So the first thing we've got here is, so we've got a multiple choice quiz. The student takes a quiz with 4 multiple choice questions, each with 5 possible answers. And so the first thing is we should probably check. I'm telling you it's a binomial distribution, but you probably shouldn't take my word for it. You probably should check it out on your own. So in this case, our number of trials fixed. Yes, there are 4 of them. So our N in this case is going to be 4. So is there a probability of success? So the success would be getting one of those 5 answers correct. So either you get the right answer or you get the wrong answer. So even though there's 5 choices for answers, again, if A was the right answer, it doesn't matter whether I picked B or you picked C or someone else picked D and someone else picked E. The fact is it's wrong. So that's all that matters in this case. So success would be a correct answer. Failure would be a wrong answer. So in this case, since there's 5 possible questions, then the probability of success is going to be 1/5 in this case, or if you want to write it as a decimal, 0.20. So the probability of failure is going to be, I should be writing this as 1 minus p, sorry. 1 minus p, so we're going to get 1 minus 0.2, which is 80%. So there's about a 20% chance we're going to guess the right answer, and 80% chance that we're going to guess the wrong answer. And again, just because I got the first question right doesn't make it more likely I'm going to get the next question right. So these are independent events, and I want to guess correct answers. So I've satisfied the conditions. This is a binomial distribution. So what I want to do first, and again, you'll see we don't actually have to do this for problems, but I wanted you to kind of see how it works just so we could fill out the actual probability distribution function for this chart, just so you could see where the answers were coming from. Again, for these problems, we won't really need to do this, but I thought it'd be a good example. So what I want to do is I got to remember that n equals 4, my p is 0.20, and what I'm going to do is I'm going to go through and change out these x's each and every time. So I'm going to calculate x equals 0, x equals 1, 2, 3, 4, 5, using binomial PDF to fill out this chart. So let me flip over to the calculator real quick. And so clear this out. So first we need to figure out, well, where is binomial PDF on the calculator? So what we're going to do is we're actually going to go to this, I hit it by accident. So the vars button, but we don't want the vars. We actually want the second vars where it says DISTR, so distribution. That's what that stands for. And so we're doing a binomial distribution. So that's why we want to be under that menu. So hit second vars. And if you look, there's a bunch of stuff in here, and we're going to use a lot of these other ones later on. But the two that we're interested in are A and B. So Binomial PDF and B Binomial CDF. So let me click on Binomial PDF. And so on mine, notice it actually gives me a little hint that I need to do N first, then P, then the X. So if I remember, there were 4 questions, comma, a 20% success rate, comma, 0. So in this case, the probability of me getting none of them correct is 0.4096. So let me go back to the chart, and in my first position, let me put 0.4096. So I've got about a 41% chance of getting them all wrong. Doesn't sound not too bad, I guess. So let me go back here and now do the same thing. So I'm going to cheat a little bit. If you're using Binomial over and over and over again, especially like I'm doing, if I just hit second enter, it'll allow me to pull the same command up again. And this way I can just go in and change the 1 and then hit enter. And so again, it's a 0.4096 chance of getting the second one right, or just one question correct. So 0.4096. So let's do this again. Change it to 2. And so now it's increased. So now we've only got a 15% chance of getting 2 exactly correct. So 0.1536. So let me switch back to here. And then do it again for 3. So 0.0256. So it's getting worse and worse to try to get a better score. So I'm definitely better off. We got a better chance of failing this maybe than I do of passing. So 0.0256. So let's do 4.0016. And then finally, oops, do 5. And so according to this, I've got a 0% chance. I wonder if I'm rounding these or something. Doesn't look like it, so doesn't look like I'm using any. Let me see, let me put them in auto mode for a second. No, it still gives me 0. Okay, so the probability of getting all 5 of them correct is pretty much 0. So I just wanted to verify. So at this point, we probably should add these guys up. And it does look like it doesn't add to 1. So in reality, these should add to 1. So I'm a little nervous that maybe it was rounding some of these answers in the beginning. Let me check 0 again. 0.4096. Oh, I know what the problem is. I know why it's 0. Duh. Ignore me. I've only got 4 questions. I was thinking about the multiple choice parts, so this won't actually occur in this case. So the fact that because you can't get 5 questions right when there's only 4 multiple choice questions. So this shouldn't even be a column. So that's my bad. So I totally screwed that up in this case. So in this case now, these should add up to 1. So sorry for screwing that up totally. But, all right. So now what we want to do is we want to look at some of the different possibilities. So what's the probability that a student gets exactly 3 correct? So in this case, what we're looking for is this is the probability of big X is exactly 3, or sometimes you'll just see it written as P of 3. So in this case, since it's exact and we've written out the whole chart, all we're doing is we're just grabbing that value off of the chart. So in this case, the probability would be 0.0256, or if you wanted to, you could change it to 2.56%. So however you want to do it. So for me, like leaving it in decimal form is fine. You don't really have to switch it to a percent if you don't want to or anything. So now what if we want to do what's the probability that a student gets at most 3 correct? So that the biggest thing, so he gets the biggest value he gets is 3, but he could get 0 correct, he could get 1 correct, he could get 2 correct, or he could get 3. So from inequality perspective, this is going to look like x is greater than or less than or equal to 3. So again, there's kind of two different ways you could do this. You could actually go through and say, okay, well, let's calculate p of 0 plus p of 1 plus p of 2 plus p of 3, especially since we have the chart, and just add all these guys up together. But in this case, like, we could also use our binomial CDF, because remember, this is exactly what binomial CDF is programmed to do. It actually allows us to figure these guys out exactly. So if we look, let's go back to binomial CDF in this case. So again, I'm going to have to hit second distribution, binomial CDF. So I'm going to type this in exactly the same because I still have 4 questions. My probability of success is still 0.2. But in this case, I want to go up to 3. So now this is going to add all those values up from 0 to 3. And it looks like I get 0.9984 in this case. 0.9984. And so if I kind of look, the only one I'm actually missing out of my binomial distribution is the 0.0016. So if I were to add this to that, that would give me a total of 1. So it looks like binomial CDF really did what I wanted it to do and added up those first 4 columns for me and gave me the probability that someone gets at most 3 correct, or 3 or less correct. All right. So what's the probability that someone gets less than 2 correct? So in this case, since it's strictly less than 2, then that's going to look like big X is less than 2. So again, I could do this 2 different ways. If I had the chart written out, I could do probability of 0 plus the probability of 1 and just add those 2 guys together, and that's going to work perfectly fine every single time. Again, I don't want to do 2 because I don't want to include 2 in my answer, so that's why I've only done 0 and 1. But if I wanted to do this using binomial CDF, say, for example, what I have to do is tweak it a little bit, because remember, binomial CDF is always strictly less than or equal to. So if I kind of drop it back, then what I can do is I can actually include just 1, because if I go up to 2, it's going to actually give me the whole entire thing. So the way I want to think of this, instead of as x is less than 2, which is true, I want to think of this as the inequality x is less than or equal to 1 in this case. Since we don't have decimals or anything like that in our x values, it's safe to say that, because the only values that I'm going to get are just 0 and 1. I'm not going to pick up 1.5 and things like that. So it's perfectly safe to use this notation. So what I'm going to do is I'm going to type this in as binomial CDF 4, 0.2, 1. So again, even though my original question involved a straight less than, if I convert it and think of it as a less than or equal to, then I can just kind of rewrite it and put the 1 in there in its place. So let me go back to the calculator. And so again, I'm using binomial CDF. So let me just pull it up. So the first 2 numbers are exactly the same, but in this case, I just want to go to 1. And so when I hit it, I get 0.8192. Oops, sorry. And if I happen to look, what happens if I add 0.4096 and 0.4906, 0.8192. So they're exactly the same. So again, there's a couple different ways you can answer all these questions. So just kind of keep that in mind. So, because sometimes you have to get a little creative with the binomial CDF to get the answer that you want. All right. So we've kind of answered the equals, we've answered the less than or equal to, we've answered the straight less than. So if we kind of scroll back up to our chart, we've solved this kind of problem, and now this kind of problem. So I'm assuming these other ones are coming up. So let's go down. I don't want to, keep you in suspense for too long. So let's go check here. So what's the probability that a student gets at least 2 correct? So at least is the same thing as 2 or more. So from an inequality perspective, this is going to look like greater than or equal to 2. So again, if I were writing this out in terms of just like individually, I could do it this way. And again, this is going to work perfectly fine. So probability of 2 plus the probability of 3 plus the probability of 4. Oh, well, there's no probability of 5. I keep messing that up. So there we go. And I could just add those guys straight up off the chart, and that would give me exactly the answer that I'm looking for. So I'd get 0.1536 plus 0.0256 plus 0.0016. And that would give me the exact answer I'm looking for. But again, how could I do this using binomial CDF in this case? Well, again, the nice thing to remember is binomial or probabilities always add up to 1. So what I can do is I can actually think of this as a 1 minus situation. And I can go 1 minus binomial CDF. And so remember, the things that I don't want are the things that aren't written down. So in this case, I don't want to include 0, and I don't want to include 1. Those are the things that I want to subtract off in this case. So I want to keep 2, 3, and 4. So what I want to do is kind of what I did above. So I want to end with 1 in this case. So what I can do is I can write this as 1 minus binomial CDF 4 comma 0.2. And again, I don't want to go up to 2 because I want 2 to be included in my answer. So I want to end at 1 because remember I'm adding up to that value. So I want to add up to 1. And whatever I get from there, that should be the same thing as adding P of 2 plus P of 3 plus P of 4. So let's check it on our calculator just to see if it works. So again, I'm lazy. I'm just going to pull this straight up again. So hit second enter and then cursor in front and do second insert 1 minus, because again, I'm like super lazy. And so I already have the 4 comma 0.2 comma 1. So let's hit enter. And so we get 0.1808. So let's jot that down here. So 0.1808. And so let's verify. What is P of 2? So P of 2 was 0.1536. P of 3 was 0.0256. And P of 4 was 0.0016. So let's just add these together real quick just to make sure it's true. So 3 sixes is 18. 5, 8, 9, 10, 7, 8. Oops. Oh, I don't carry any, so I guess it helps if you actually add it correctly. So 0.1808. So lo and behold, I got the right answer. So again, this is where you have to be pretty creative with some of these guys and make sure we're getting the right 1 minus and things like that. But that's how we'll get around answering these kind of tricky questions and stuff. So hold on, my battery's about ready to die. I'll finish this problem up once I charge up a little bit here. I don't want to lose this. So I'll make another video to capture the rest of it. So